Okay, this chapter is thermal properties of the material, and the first topic is the heat capacity, mean amount of the heat energy required by any substance to change its temperature per unit Kelvin is called heat capacity. So heat capacity changes temperature. So when temperature changes, kinetic energy of the substance changes, but potential energy remains same because there is no change in the state of the material. Heat capacity is equal to heat energy divided by change in temperature. Heat capacity is represented by capital C, heat energy by Q, change in temperature delta theta. Q is the energy in joule, change in temperature in A level measured in Kelvin, so joules per Kelvin. Now, if heat energy is constant, then heat capacity and the change of temperature both are inversely proportional to each other, mean the material with larger heat capacity will increase its temperature less. Now, the next is the specific heat capacity, amount of the heat energy required per unit mass substance to change its temperature per unit Kelvin is called specific heat capacity. So heat capacity, no mass given, but in specific heat capacity, mass is mentioned. So it is for 1 kilogram substance. So mass is specified. That's why it's specific heat capacity. In heat capacity, no mass is given. Mass is not specified. So specific heat capacity is heat energy divided by mass divided by change in temperature. So specific heat capacity, small c, heat energy Q, mass M, change of temperature delta theta. So joules for the energy, M kilogram, delta theta Kelvin. So this joule per kg per Kelvin is a unit for specific capacity. Now, if this heat energy is constant, mass constant, then specific heat capacity is also inversely proportional to the change of temperature. It's similar to heat capacity. But when this formula is written like this, specific heat capacity 1 over m q divided by delta theta. So this q divided by delta theta is heat capacity. So the relation is specific heat capacity 1 over mass times heat capacity, mean mass and specific heat capacity product is equal to heat capacity, mean mass multiplied by specific heat capacity is equal to the heat capacity. But the specific heat capacity of the substance remains same. Like water, it is fixed, it's constant, 4.2 joules per gram Kelvin, which can be written as 4200 joules per kg Kelvin. When this is constant, then mass and the heat capacity both are directly proportional. When graph is plotted, heat capacity at the y-axis, mass at the x-axis, then straight line passing through the region, so the gradient is specific heat capacity. Now, first formula, which is heat capacity, can be written as Q divided by delta theta, but for the numerical, we will write it in this form. Q is equal to C delta theta. And number two, specific heat capacity, Q divided by M delta theta, but for the numerical, we use it like this, MC delta theta. This C capital is the heat capacity, this small c is specific heat capacity. Now the problem is, if this is the substance, its mass is mentioned m, its initial temperature suppose T1, and heat is supplied. In previous classes, in O level, it was assumed that no energy is lost in the surrounding. Whole of the energy is absorbed by the material. So we use Q is equal to mc delta theta. Mean whole of the energy Q is supplied to the material. Then we can use formula Q is equal to mc delta theta. But practically, when heat is supplied, some of the heat energy is lost and the remaining is absorbed by the material. So while calculating the formula, this Q is equal to mc delta theta, means C small, specific heat capacity, Q divided by m delta theta. So practically it is absorbing less energy. Look, this is absorbed, is smaller than supplied, but when this is ignored, we are using here the whole energy which is supplied. So that's why this answer C is wrong in practice, right? So when we will ignore the loss of the heat energy, we are using the large value than the actual, then the all calculations for C is wrong. So the value of C will be overestimated. Mean the answer will be greater than the actual if it is ignored. So practically, less energy is absorbed. When loss is ignored, the answer for the specific heat capacity will be higher than the actual, and it is called overestimation. So when heat is lost in the surrounding, it is ignored, then all calculations of the specific heat capacity or heat capacity will be overestimated. Now, this loss of energy mean the rate of flow of heat to the atmosphere, to the surrounding. It depends on the change of the temperature. There is no significant change during the experiment in the atmosphere. So we will assume that the rate of the flow of the heat is constant. Mean same amount of the heat is absorbed by the surrounding in all experiment. So for the rectification, for the correction of this problem, this overestimation, we will perform the experiment with two different masses. For example, mass M1 of the material, mass M2 the material, and we will use the same heater. So the power of the heater is same, masses material different. So according to the formula, Q is equal to mc delta theta, which is absorbed plus lost L. Now, initially for the first material, energy which is supplied is IVT1 M1C delta theta plus L. When we are keeping the change in temperature constant, then the same amount of the energy is lost every time. Now, next time, we will use the same material, same metal of the different mass. So definitely, the heater will take the different time to rise the same temperature. So for the next experiment, it is IVT2 because the mass is different, but the loss of the heat energy is again same. Reason? The rate of flow of the heat energy to the surrounding depends on the change of temperature, and we are keeping the temperature change same. That's why the law is same. Now, two equations for the same material mean same specific heat capacity. We are keeping the change of temperature constant, only changing the mass of the material. So, I VT1 M1 C delta theta plus L, and next IVT2 is equal to M2C delta theta plus L. Now subtract second equation from the first. So this is cancelled. So it becomes IVT1 IVT2 M1 C delta theta minus M2 C delta theta. So it can be written as IV common T1 minus T2 C delta theta common M1 minus M2. So the specific heat capacity C will be equal to then IV T1 minus T2 divided by delta theta M1 minus M2. So this is the formula to get the exact value of the specific heat capacity. So here, this overestimation of the value of the specific heat capacity is corrected.